Hello, welcome to Sigmoid Tech Talk. I'm John Daniel, working as a senior data scientist in Sigmoid. Today we'll be discussing about a case study of matched markets. The solution was provided to a client who is a global leader in health and hygiene products. The problem statement was that the marketing teams across the globe needed a data-driven approach to test out new campaigns on a smaller scale and then eventually scale it up based on the results. Hence, we came up with a solution called Test and Learn. In this, a pilot campaign is activated in a smaller region of the market, and the returns are calculated for the same to see if the campaign was effective and if it can be scaled up. The process can be divided into two parts: pilot design and measurement. In pilot designs, we have two models: matched markets, in which we identify similar regions in the market to define test and dark regions. Test regions being the regions where the pilot campaigns will be activated, and dark regions being the control regions where no media activation will be happening. Then we proceed to the budget estimation model where we come up with the budgets for the pilots to run on the test regions. Post that, the pilot execution happens and we proceed to the measurement phase where we use several concepts like Shapley to calculate the marginal contribution of different drivers towards sales and hence calculate the returns to measure the success of the marketing campaign. Proceeding to the match markets. So MMT is a community clustering approach to identify regions similar in terms of various KPIs, but in our case, primarily based on the weekly sales. The input to the model has is divided into three categories: primary KPIs, which consist of weekly sales for all the regions; secondary KPIs, which consist of promotional sales, number of stores, distribution data, etc., and informative KPI, which consists of audience size and population. Moving to the first step of MMT, the dynamic time warping. After identifying the primary, secondary, and informative KPIs, we do a DTW treatment on the primary KPIs, and then we calculate the Pearson's correlation coefficient for all the region pairs for original as well as the DTW series. We will be covering dynamic time warping in our session 2. Proceeding to the next step, we go to the community clustering, where for several iterations we apply different thresholds on the correlations and generate a graph object from the region pairs after removing loosely correlated regions. And then this graph object is passed to the Leiden's algorithm to identify communities. The iterations continues till enough regions are available in the largest community. So as part of an output, we get a list of communities, and each community cluster consists of different regions. And the descriptive sales statistics, such as mean or average of the sales, total sales, and interquartile range, which is basically the difference between the 75th and the 25th percentile. Apart from that, we also overlay information regarding the secondary and informative KPIs, such as the percentage of promotions done on the regions, total population, and total sales per population. Thank you. We'll be seeing you in session 2. The basic problem statement for MMT was that we need to identify regions that are very similar in nature with respect to sales. Hence, we use Pearson's correlation coefficient to measure the association. It is used to measure how strong a relationship is between two variables. Here is the formula for Pearson's correlation coefficient. It returns a value between the range of -1 and 1. 1 indicates a strong positive relationship. For example, we could consider the promotions and sales of a product. So if the promotion goes up, the sales of the product is expected to go up, hence a positive correlation coefficient value. For a negative -1 indicates a strong negative relationship. So for this, we could consider the average price and sales of a product. If the average price is increased, the sales is expected to go down and hence a negative value. A result of 0 indicates no relationship at all. For this, we could consider any two unrelated features such as sales of a product and average price of a different product. There are a couple of drawbacks for Pearson's correlation coefficient. So if the trends of the two series are out of sync, or if there's one to many or many to one mapping present in one of the series, the coefficient value will come out to be a bit low. Hence, we apply a dynamic time warping treatment to better align the two series. So DTW is an algorithm to measure similarity between two temporal sequences. It can compare arrays with different lengths to build one-to-many and many-to-one mappings in order to reduce the distance between the two series. Here are a couple of rules and regulations for DTW. So every index from the first sequence must be matched with one or more indices from the other sequence and vice versa. The first and last index from the first sequence should be matched with the first and last of the other, but it does not have to be its only match. And the mappings between the two series should be monotonically increasing. That is, if data point X of series A is mapped to data point Y of series B, then data point X plus 1 of series A cannot be mapped to any data point less than Y on series B. One of the use cases for DTW is sound pattern recognition. Here, the two plots which you see are basically a sentence spoken by the same person with different speed, and that's why the spread of different words is a bit different in the two graphs. But with DTW, we are able to match this properly. Here's a demo example of dynamic time warping. For the raw inputs, we have two series, and from the graph, it's visible that the trends of the two series are out of sync. Hence, we get a coefficient value of 0.69. So on applying DTW, we can do one-to-many and many-to-one mappings. For example, the index 1 of series 1 is mapped to the index 2 and index 1 of series 2. And the index 2 of series 1 is again mapped to the index 2 of series 2, and so on. So after doing the dynamic time warping, we can see that the trend is matching well and we get a coefficient of 0.95. In the below graph, we have vertically shifted one of the series to see the trend match. Here's the example of the DTW in working for the MMT use case. So as an input, we have the week IDs for the first column, and we have the weekly sales data for four different regions, N1, N2, N4, and N7. Just getting the Pearson's correlation for each region pair, we can see that there are a couple of regions where the correlation is not that high. For instance, N1 and N4 has correlation of 0.87. N1 and N7 has a correlation of 0.80 and so on. So after applying the dynamic time warping and again calculating the Pearson's correlation coefficient, we can see that the poorly correlated region pairs such as N1 and N4 has better correlation now. So it increased from 0.87 to 0.93. Similarly, for N1 and N7, it increased from 0.80 to 0.84. Thank you. We'll be seeing you in session 3. So community clustering is a network analysis technique used to identify a group of nodes in a network that are densely connected to each other. In the plot here, you can see the individual circles that we see are nodes, and the edges between the nodes are basically the connections between them. So the aim is to uncover hidden structures or patterns of relationship within a community. So we start the process by randomly assigning each node to a community, and we iteratively optimize a quality function by reassigning the nodes. And once the quality function stops changing, the final list of community is generated as an output. So in our use case, after the second step of MMT, where we do the dynamic time warping between the regional sales, we get the correlation of the time warped series, and here is the intermediate input that will be passed to the graph to generate the graph. So here we have the pairwise correlations between each region, and we perform several iterations by applying certain thresholds to filter out loosely correlated regions. So let's say if we apply a correlation threshold of 0.92, here are the highlighted region pairs which will get selected and others will get dropped off. So apart from region D, we can see that every region is connected to at least one of the other regions, but D has no connections at all. So assuming these are the nodes in the graph without any connections, once we get the connection from the correlation thresholds, we can see that A is connected to F, B has connections with to C, E, F, and G. So on applying the connections, the graph looks something like this. So this graph is then passed to the Leiden's algorithm to generate the community. And it's evident from this that there will be like three communities generated, one consisting of the four regions C, E, and G, and B, and the other consisting of regions A and F, and region D will be a separate community. So this is the list of community that we'll get as the output. Here is the raw result from one of the use cases where the requirement of number of regions in the largest community was 6. And the pilot design requirement was that we should have 3 cells, specifically 2 test cells, where the pilot campaign will be activated, and one dark cell, which will be the control region of the study. On further analyzing the results, we can group regions F and G together to generate the 3 cells mentioned here. And the idea is to keep all the KPIs on a similar range between among the 3 cells. So it's evident that, yeah, this 3 cell selection seems to be fine. At last, we do a sanity check and see if the correlation across the cells also are good enough. So in this case, you can see that region G had a bit of bad correlation with region A, but when combining them together along with region F, the correlation improved a lot. So these cell classifications are good to go. So this is the end of match markets phase. Then we proceed to the second phase of pilot design, which is the budget estimation, where we estimate the budget for the test cells to run the pilot campaign. And post the pilot execution happens, we get the measurements and the returns of the pilot campaigns to see how it performed and if it can be scaled up on a larger level. Thank you. This is all about the case study match markets.